Okay, hello and welcome to the Chapter 8 webinar. This should be the part 1. There's going to be several parts of this chapter webinar instructional information here. But this is the first opening of it, and this is all about solution chemistry. And although there's only 2 words in the solution chemistry, this actually encompasses a pretty wide range of material. So this is going to be a really important one to pay attention to. I've worked out some really important details, especially later throughout this webinar, that will help you in your homework or just overall understanding, complementing the book material or whatever other materials that you are using to help you study and prepare. Okay, so let's get into it. So there's 7 primary topics, I guess, within this chapter. The first one is transport across cell membrane, and then you have osmosis and diffusion, solutions, colloid suspensions, solution formation, chemical equations and stoichiometry, concentration and dilution. So this is a lot of information, and we're going to be going back to stoichiometry, of course. You see the word here. So this, harkens back to what we were doing in, several weeks ago, I guess, back even into chapters 1, 2, and 3, in fact. So we're going to be going back to that level. Now, I want to start with transport across cell membrane. In your book, this is listed last, but I think that because we just finished chapter 7 and there was a lot of really good information about the phospholipid bilayer and membranes and of the cells and such. So I wanted just to continue on because, well, that's the same kind of train of thought that we just ended with. So let's begin it with here as well. So here's the cartoon. Again, this is a chapter 7 cartoon, and I'm reliving this example because it's pertinent for solution chemistry, transport, all these things. So if we look at the phosphobilipid layer here, again, you have the area outside the cell, which would be to the top of that bilayer. We have the inside of the cell, which would be shown beneath this bilayer. Here you have this tails, which definitely indicate that we have nonpolar groups, and they are oriented towards each other. Within that nonpolar region, you have cholesterol molecules, which are going to be listed here in yellow. I didn't highlight them yet. And then we also have protein channels. Some of them go all the way through from the inside of the cell to the outside of the cell, and some of them just remain within the inner surface there, or even outer surface, I guess, if you will. Then, of course, you have some of your glycoproteins and your glycolipids that may be residing outside the cell. The polar head groups are denoted by the spheres on those nonpolar, phosphobilipid, nonpolar polar cartoons, and that's just the same. So there's nothing different here than what we've already talked about. You know that this phosphobilipid helps provide cell structure. It also provides boundaries, regulates ions, proteins, and other components. And you have your nonpolar groups, and I just highlighted those. Again, it's important to note that phospholipids prevent polar molecule transport due to the nonpolar region. So in other words, if you had, for instance, sodium cation, right? And a sodium cation, when it's in a solvent or in a matrix of water, that would give rise to ion-dipole interactions, which are really strong intermolecular forces. However, although that the sodium cation might be attracted to the polar head group here, i.e. the spheres, it won't be able to pass through to that nonpolar region where the tails are, to get to the outside of the cell, or vice versa, from outside to inside. In order to make that happen, you're going to have discussions about what are these tunnel transporters. So like all these protein channels that can emit that. And so that's kind of where I want to start. So here you have several different transport processes that happen through a membrane. And these are the ones that we want to talk about. So you have, first of all, passive diffusion. And this is very simple diffusion. This is most flexible because the material that you're talking about, all that physiological material, whether it's oxygen, carbon dioxide, and such, it doesn't matter if the polar head group is present or if the nonpolar region is present. It can actually get attracted to the polar head group, pass through the nonpolar, and then continue on inside the cell, of course, or outside the cell. You also have the channel formed by the integral membrane protein, which I was kind of alluding to before with the sodium ion. If, how is that going to transport from inside the cell to outside, or, vice versa, outside to inside? Well, there's going to be a protein for that, and it's going to open up with some additional constraints. And then you also have active transport, which active transport is one of those where it's going to involve energy. So as an example, what would be an example of passive, or what's also considered to be simple diffusion? Small nonpolar molecules. So things like oxygen, nitrogen, and carbon dioxide. Cholesterol and steroids actually can also do this, and part of the reason is because they have the combined character of the polar and nonpolar groups. So that's also very important. So not only small molecules, but also ones that have kind of a multifunctional aspect to its molecular structure. Well, in terms of polarity anyway. With respect to transport formed or gone through with through a channel with the facilitated transport, here you have examples that I just alluded to earlier, ions like potassium, chlorine, sodium, things like that. You also, from this list, see that the valency of those ions doesn't matter a whole lot. In other words, you can have calcium 2+ and magnesium 2+. And not only that, but the charges also don't matter. You can also have chlorine ions, right? The chloride species also being passed through, as well as the bicarbonate species. So these are very robust transport proteins, channels that exist within phosphobiolate layers. Of course, certain proteins are going to be responsible for certain passage of certain ions. Additionally, polar molecules are also able to be transported. For instance, glucose. Glucose is a polar molecule. It has extensive hydrogen bonding environments, right? The OH groups, and that will actually have facilitated transport into and out of cells. The final one is the active transport, and what would be an example of that? Well, how about potassium or proton? ATPase, which modulates the amount of potassium and hydrogen concentrations that are found in the stomach. So this is the ATP, this particular active transport channel here, you would call this a protein channel pump, or ATPase, for instance, would be able to help assist with that transport. Usually, if there is an overexpression of potassium or H+, right? And we're referring to that as a cation, or as a, you could say hydrogen cation, but you wouldn't. You'd call that a proton. You would have medicines that can help you modulate that kind of behavior. So for instance, Pepcid, Prilosec, Tagamet, they block production of the proton inside the stomach. So all those gastric acids that are produced, obviously that's where the proton, the H+ is deriving from. And so these medicines help restrict the production of a lot of that gastric production. So that's the interesting part about there. Again, always remember that active transport requires ATP, okay? I don't know whether you want to remember that as active with A from the ATP or not, but just know that the ATP energy is going to be required in order for that to happen. Now, another aspect, another example here would be, let's look at the chemical synaptic transmission of signals, electrical impulses. So here's a huge cartoon of neurons, and shown are the electrical impulses that flow along the axon. You have all these dendrites, and they help, spread that electrical signal out. And what's going to be interesting, and what I want to take a look at here, is what's going on in that bulb there. So where you have the receptors, you have the neurotransmitter molecules, you have synapse that exist. So let's take a closer look then at what is going on. And so the neurotransmitter of choice then for this kind of signaling will be acetylcholine, ACH, and we've already talked about that before. So we already know that we've introduced the passive and the active, and then the facilitated transport of species. In this particular case, facilitated transport, it's formed by the integral membrane protein, and it's going to help this out. So the acetylcholine structure is shown there. And you can see that this is a polar molecule. Of course, the direction of the polarity is going to fall along the quaternary ammonium site here. But what you're going to look at within this cartoon is this bulb or this axon terminal, and then of course the dendrites. We had introduced the synaptic cleft previously in that cartoon, and just to let you guys know, just for interest's sake, it's about 20 nanometers wide. In other words, the region between that bulb of the axon and the dendrite. And what you have here are a bunch of other components. You have obviously postsynaptic density, because that's where the signal is going to be delivered to, and the purplish kind of paired up molecules, well, that's calcium gated channel. Okay, the synaptic vesicles are going to be denoted by the spheres, and within these spheres you have the acetylcholine, again denoted by the ACH. And these vesicles, again, I want to remind you, and this is going back to chapter 7 information, but these are natural structures, and this is what it looks like. You can also call it a liposome, but the vesicle is the natural version of that, if you can recall. So you have the polar inside, you have the polar outside, then you have this non-polar layering within the middle of that vesicle. So that's what these spheres are representing. And within the middle of that vesicle is where the acetylcholine resides. And you have these transporter proteins as well. So these are the transporter proteins. Basically, these are the integral membrane proteins that are going to help the facilitated transport of acetylcholine from the axon terminal here in this bulb to the dendrite. In other words, this is what's going to help provide that electrical signal, at least the continuity of it. So let's go on from here. So if we, and I have this region here boxed out, this is going to be one of the most important regions for what I'm going to discuss in just a moment. It's not necessarily about it performing properly, but what's going to happen whenever it becomes potentially impaired. So let's get to the point here. So the signal arrives at the axon synapse knob. Okay, that's the first part, and that's going to obviously occur where that knob is. The calcium gated channels open and calcium flow into the synapse knob. Once that happens and enough accumulation of calcium occurs, then it's going to push the acetylcholine loaded vesicles, again denoted by those spheres, to the axon presynaptic membrane, which is going to be near the surface here, where you see that you have, for instance, that facilitator membrane protein. You have that cut out at the bottom of that bulb, and then you also have like that paired up calcium gated channels. The vesicles will then discharge the acetylcholine into the synaptic cleft. In other words, that gap, that 20 nanometer gap that resides between the top and bottom structure. Now, at this point, the acetylcholine will diffuse in cleft and fit into specific receptors on the postsynaptic membrane. Those receptors kind of look like wrenches here, almost like, you know, or arms, I guess, if you only had like 2 fingers, or if you were to cup your hands, I guess, and have them open, right? Those are the receptors, and those are going to receive the acetylcholine. Those exist in the postsynaptic membrane. What is that part of? That's part of the dendrites. So that will receive it. Now, at this point, this is where the boxing comes in. This is where interruption of that signal can be detrimental to your body function. For instance, with the paralyzing poisons that were found in South America and that are still used, the curare, as they're often known, and what that does is that all that plant alkaloids that provide that kind of paralyzing effect, they compete with the acetylcholine in those receptor spots, and so they basically flood it out. If they flood it out, then the acetylcholine can't get collected in those receptors, and you have this curare, essentially these plant alkaloids that have settled into there, and that's what's going to give rise to a sudden paralyzing effect because the signal has been interrupted. The electrical signal has been interrupted. So whether that's breathing, whether that's chewing, whether that's talking, whether that's even moving, whatever is going to require electrical signal, which is, by the way, a lot, right? Your breathing, your muscle movement, I mean, all that stuff, that it's going to have a very detrimental body effect. So that's where that pain is. So you guys know that I've already introduced this kind of action before several chapters ago, but I'm coming back to it because I think that it makes sense here. And I think that if you're taking your physiology courses, this might also help with that too. Just understanding of that, it's just maybe a different way of looking at it perhaps, but I still think it's pretty important and kind of neat. Anyway, so let's assume that there is no plant alkaloid in there that's going to interrupt the collection or the reception, I guess, of those acetylcholine receptor neurotransmitters. And let's move on from 5 to 6. So we're going to assume that, again, the receptors receive the acetylcholine. Once received, the ligand-gated channels open and sodium ions then diffuse out into the dendrite. So now we have a different cation. So instead of calcium, which was required in order to actually open, right, the synapse knob and allow the vesicles to be opened and have the acetylcholine be transmitted into the cleft. Now, once the dendrite receives it, sodium cations now within that postsynaptic cleft or postsynaptic membrane are going to be able to continue that electrical signal. And so once sufficient cations of sodium has entered, then the acetylcholine will detach and then it'll be hydrolyzed by an enzyme. Okay, on the next slide, I'll talk a little bit more about that. But it's about acetate and choline metabolites combined by choline acetyltransferase. And once they recombine like that, and the acetate species, that may even come from another area. So it's not like the breakdown of acetylcholine is going to create this acetate and choline, which it does, but then it's just going to recombine. Actually, the acetate is going to be derived from coenzyme A often, and that's going to combine then with the choline metabolites that were created by action of this ACH, or I guess you could even call it the ACE. It's an enzyme that will hydrolyze that, and they will recombine in order to continue that process to yet the next axon, right? So you're trying to communicate the electrical signal. This is just one snapshot of that, but it has to continue on or else that electrical signal will be lost. So just think of it as like a string of pearls, I guess, if you want, or even some kind of connection like a string of light bulbs, I guess, Christmas lights. And what I'm showing you here is just one of those light bulbs. Whenever things are going to reconvene and recombine so that we can have acetylcholine again wrapped in these vesicles, it can then be transported, you know, from the knob into the cleft, into the postsynaptic membrane of yet another species. So that's basically the communication of electrical signal. If we were to look at what that receptor would look like, by the way, and I know we just said, hey, look, that looks like, you know, hands opening. This would be a cartoon of it. You have 1, 2, 3, 4, 5, basically protein clusters, and then inside you have a gap. You have some empty, it's like the eye of the hurricane, right? So, you know, you would just call that the pore. If you were to fill it out with actually the protein structures and stuff with the ribbons and the helices here and things like that, well, this is what it would look like, you know, and all those have different properties. And that's one of the reasons why they're given alpha and beta and number characteristics. That's not as important for you guys, but just wanted to show you what that would look like. So the figure on the far left then is the top view. Then this figure A in the middle here is also a top view. B is a cross-sectional view, okay? And so this is where the origination of having the hands being cupped kind of looks like. So you have this this cluster of proteins that are wider at the top and narrower at the bottom. And by the way, if you guys looked at the other webinar from chapter 7 early on, we talked about the coronavirus. This almost has a similar looking shape only to the spike proteins, which the coronavirus uses to attach into the cells of the host, you know, i.e. us. So just to let you know that this vestibule, that's also another fancy way of saying pore, has about a 40 angstrom narrowing within the dendrite, and it's about 20 angstroms wide. So very small regions here that we're talking about. In case you want to even know about how far these receptors stick out from that postsynaptic membrane surface, well, 60 angstroms. So 60 angstroms, it extends into that cleft, into that opening between that knob and that postsynaptic membrane. The lipid bilayer, again, because we're talking about cells and stuff, and even axon, electrical conducting cells, there's still types of cells, and they do still have the phospholipid bilayer, and that's what you're looking at here with the gray. So you have the obviously this bilayer present, and this is a top view, actually, this TEM, so this is really high resolution. So the resolution on this, you can know that these gaps within the pore about 20 angstrom wide within the sun, inside of there, you can see how this TEM image definitely helps to resolve some of the overall receptor shape, but it can't get, to the degree of 20 angstroms at this point. But here is, another way of showing that, closing in on it here, and that is all you need to know about that. But it's kind of interesting, and obviously you can look at it a little bit more for, if you're curious. But let's continue on. Okay, so we talked about the enzymes that can break, but then there's also the enzymes that can recombine to make acetylcholine. So one can break it, and we can call that the ACE, and that's the acetylcholinesterase. Okay, it hydrolyzes ACH into metabolites. Basically, this almost appears, right, as an ester. And so what can that, be broken down into? Well, it can be broken down into carboxylic acids and alcohols. And so you can see that this acetylcholine on the far left has that kind of structure. Obviously, it's charged. It has this quaternary ammonium species here, so it's not a true ester, but it has ester-like properties. And that's one of the reasons why this is called acetylcholine esterase in terms of what this enzyme is, because it helps to break this ester-like neurotransmitter down into the first metabolite here that you have with the negative charge. That's the acetate anion. If you had a hydrogen attached to that, then you would have acetic acid, and acetic acid is a type of carboxylic acid. And then you have also choline, and choline has the hydroxyl group attached to the rest of the molecule, and the OH group indicates that you have an alcohol present. So this is a really important comment on this, because we've been studying all of these different types of reactions, and here it is again coming to the forefront. You have this ACE enzyme, which is breaking down this ester to form a carboxylic acid and alcohol metabolite combination. Now, there's another type of enzyme that can repair or recombine some of these metabolites to go ahead and reform the acetylcholine neurotransmitter, i.e. this ester. So it does that by taking this acetate species, not necessarily from from the metabolites that were constructed whenever this ACE enzyme did its magic here on the acetylcholine, but it actually gets that often from the acetylcoenzyme A. Okay, and so what does that look like? Well, we'll talk about that in later chapters, but I have given you some of this, some of these swirly protein-like structures here, these cartoons in the upper left that represents essentially the ACE enzyme, and the one on the bottom right represents the acetylcholine esterase transferase, the chat. So you have the ACE on the upper left, and you have the chat on the bottom right. So where is the chat produced? Well, it's produced in the neuron body and deposited in your membrane. That's good, because obviously if the acetylcholine is being broken down, we're going to need those metabolites to reconvene in order to continue that electrical signaling. So I hope that you found that interesting. I think it's always interesting to try to give it some practical meaning, and I'm hoping that may have also helped you perhaps with your physiology understanding of some of the physiology of the nerves and whatnot. So I know that's a big area that you guys have to know about as well. All right, so now we're going to segue, and we're going to be talking about cellular membranes and osmosis. If we were going to do a lab, I have a really neat lab that we were going to do that was going to involve some gummy worms and such. And if you were to put those in hyper or hypotonic solutions, and we'll talk about that in just a minute about what those solutions are, you would observe some really interesting characteristics of the gummy, whether it's like a gummy lifesaver kind of thing or a gummy worm. You might get a swelling of that gummy. It might even get sticky and even smaller. So it depends on what the solution that you're using is going to do. And so this is now where we're going to segue to talking about what happens with these cellular membranes, we're going to be talking about osmosis. We got diffusion, and of course, we're going to relate that to the body. So again, here is an image that you have of the cell membrane. You know now that the cell membrane is comprised of what, right? The phospholipid bilayer. Okay. Whenever we say that, it's also interesting for you to identify these cell membranes as having, although there might be some glycoproteins, maybe some glycolipids attached on the outer surface of these membranes, it's also important that you know that these membranes are soft, right? They're not comprised of this of a protein like very rigorously held and fixed kind of material membrane. In other words, cells are susceptible to breakage. They're susceptible to insult by, I don't know, different solutions, concentrations of different agents that might be in there. They are also susceptible to soap, right? Kind of like a virus. That's one of the reasons why with certain viruses, they may have a very fatty like outer membrane, kind of like these cellular membranes, but they also might have a tougher kind of outer membrane that might be comprised of proteins. And if that's the case, you got to use something a little bit, maybe a little bit more robust than soap in order to try to inactivate it. But anyway, the cell membranes comprised of the phospholipid bilayer, they do permit obviously some molecules. The first term that we want to introduce is osmosis. Osmosis is the flow of water, okay? Why do we say water? Because that's the solvent. All right, if we were dealing with another agent where we had some material of, like, I don't know, sodium chloride or whatnot, and it was dissolved in alcohol or something, then the alcohol would be the solvent, and we'd be talking about the flow of alcohol if we were referring to osmosis. So the water flow here is actually with respect to this cell membrane. Again, you see the phospholipid bilayer, you see low concentration solution, you see high concentration solution in this image, and you have the direction of the water flow given. Well, that's also means that you have high water content, relatively speaking, and you also have low water content then in the right, where you have high concentration solution. The osmotic pressure is going to be going from left to right. This has implications for the tonicity or stretching of solutions. So what does that mean? So I just used the words like tonic, right? Hypertonic or hypotonic. Let's talk about this. So isotonic solutions, that just means everything is normal. The hydrostatic conditions are fine. And this, in other words, physiological conditions, right? The way that our blood cells would naturally reside in our blood would have this kind of appearance. They almost have this, they almost look like a donut, essentially. Or even if it's a depressed donut, like if there was like something filling up that donut and somebody put their thumb on it or whatever and pushed it down. So that is one way to look at it. Maybe not the best way, but that is the general appearance of a healthy red blood cell. So in a physiological friendly or isotonic solution. So we would say that that has hydrostatic conditions, okay? Now, under hypotonic conditions, lysis may occur. Well, that's what that looks like. All of a sudden, you have this swelling up of the red blood cell. That depression that we had put our thumb through, if we were going to say that this is some kind of donut that we had put our thumb through, all of a sudden that starts to pucker up and pop out. And so now you don't have that depression in there. The cells are starting to swell to the point where they may burst. And that's the definition then of lysis, where the cells actually die, they usually burst. And so you have a greater influx of the solvent, as noted here. We have the arrows here, and I have this dotted circle around there. You have a large amount of the solvent that's passing through the cellular membrane and filling, obviously, the cell with additional fluid. So that's under hypotonic conditions. Hypertonic conditions means that the cells are going to shrivel because the fluid from the cell is going to have to leave the cell in order to neutralize essentially the solute-rich environment of that environment. So this would be an example of seawater, right? If you had a ton of seawater and if you drank a lot of that seawater, right? You can't drink a lot of seawater. If you did that, you would be admitting into your body a solution that has a much higher physiological tonicity, if I want to use that term, right? Going back to the isotonic conditions. And so your cells are going to have to try to respond to that insult by releasing fluid in order to try to regulate that equilibration of that solute and solvent concentration. Okay, so you have normal cell looking activity, you have hemolysis, and then you have crenation. Those are the two different conditions that can occur if you have a hypotonic and hypertonic condition, respectively. Okay. Let's talk about this a little bit more. So in the physiological solutions, it's about 0.90 mass per volume, okay, sodium chloride. So 0.9% sodium chloride is essentially normal saline conditions, all right? You also have, with respect to glucose solution, that concentration is about 5%, okay? And again, that's mass per volume. We're going to be talking about mass per volume later in these webinars, but it happens in this chapter because there's a lot of content that talk about solutions. You can obviously see that what we're covering so far can be pretty dense, okay? So with a normal looking blood cell, that means that if you had to apply physiological solutions externally, right? So like a glucose or a saline solution, this is the type of structure that you can want to see with your red blood cell. And this is what normally happens anyway in your body, as long as things are going okay. In other words, as long as your physiological solution in your body, right, the sodium content in your blood, and if the glucose, is right in your blood, then everything's going to be looking pretty good. If you have an unhealthy situation, for instance, drinking seawater, your cells are not going to have that nice depressing spherical kind of shape right there, right? They're going to start to shrivel. They're going to undergo crenation. Okay, drinking too much water, where you are relieving yourself of adequate amount of sodium chloride. This is one reason why some people say, well, you don't want to drink too much distilled water. And although by itself that may not be such a bad idea, especially if you're, well, and only if you're admitting minerals through other ways. For instance, like if you're eating food at the same time you're drinking that water, then it's not going to be a problem. But if you are going on some kind of weird fasting diet where you're only going to drink distilled water, you're really going to limit your intake of food and stuff, and you're going to get yourself into a situation that could be dangerous where hemolysis might occur, because distilled water, imbibition of that, leads to the swelling of the red blood cells because there's just simply not enough sodium, for instance, or chlorine present in the aqueous environment to help keep stability of those red blood cells. So you would say that even a 2% sodium chloride solution, would that be hypertonic or hypotonic? Well, relative to 0.9%, that would then be a hypertonic. So that's bad, right? If you have 6% dextrose, that's a little bit too much. That also will wreak a little bit of havoc here on these cells, stress them out a bit too much. So that's higher than 5%, so that's no good. If you have 0.1% sodium chloride solution, that's really low. Look what your physiological solution requires, just naturally 0.9%. So 0.1 is much less than 0.9, so that's a dangerous environment as well. So just to give you an idea of those kinds of levels. All right, so if we're talking about solute solution, you've already introduced osmosis, we're talking about tonicity. What in your body is really responsible for regulating all of that? Well, it's going to be related to perhaps your kidney, and this is where because I mean, if you see the title of the slide, diffusion and dialysis, the first thing you start thinking of is kidneys, right? So that's the giveaway there. But let's talk about diffusion first before we get to the kidney. We have the flow of solute, and it always moves to equalized concentrations, okay? Kind of like what the osmosis was doing as well, I mean, there's always going to be a flow of substance, whether that's the solute, whether that's the solvent, in order to try to get to equilibrium conditions. Kidney filtration does this, all right? So here's just this cartoon. And you have the blow up of the kidney bean-shaped kidney. Here you have obviously the different regions of the kidney as shown, and the important thing to note here is that within the artery, okay, so this is within the artery, the blood, waste, and water all enter here, okay? That's the main, what they call the renal artery. So these fluids get admitted into the kidney, and if the kidney is healthy, then it's going to filter out the material that is going to be too much. It's going to be excessive within your body. So if there's, for instance, too much sodium chloride that had been admitted by you because you drank a little bit of seawater, maybe it was by accident, you were swimming in the ocean, right? You got a little bit of seawater in your body. Well, the kidney is going to be able to flush that, no problem. That also goes for the same as eating, right? If you're drinking like a soda that has a lot of sugar in it, maybe a lot of salt as well, or if you're eating foods that have any kind of salt or any kind of sugar content, if there's going to be an excess, the kidney's going to help filter out that excess to allow you to continue on your day. And obviously, if there's problems with that filtering process, with the digestion anyway of those foods, that's going to be manifested clearly. I mean, you're not going to feel very healthy. So the filtered blood or excess water leave through the renal vein, which is indicated by blue, and the excess water and toxic waste are then dumped. So there's a new port here, and that's just going to leave there via the ureter, and of course that's going to be eliminated from your body as urine. Okay, so you have one in and two out, with one of those outs being related to the elimination of the waste. Whereas the other stuff going from the blue, of course, it needs to be circulated through our body because we need to be able to have the blood and the water readmitted to keep our body hydrated. Well, that's what happens. So red is unfiltered, blue is filtered, in other words, and the orange, as I noted here, or this ureter, exit point here, refers to the bladder. So that's waste removal right there. Kidney function, so important, guys. So you have not only just filtration, and here is the really important aspect of this. The kidney is so important in regulating blood pressure. So renin is an enzyme that is found in the kidney, and it produces angiotensin, which is a blood pressure protein. Okay, there's many different types of angiotensin proteins that are involved in blood pressure regulation. Renin is one of those core enzymes that helps to switch among those different angiotensin proteins. It's very important. And so if you don't have a properly functioning kidney, then problems with angiotensin may arise because maybe there's some problems with the renin production, or maybe not only its production, but it's interfacing with the angiotensin. In that particular case, it can give rise to hypertension or even further cardiovascular issues, okay? So oftentimes, there can be medicines that are going to be used to try to combat that. Okay, so, try to rectify it, I guess, if you will. It really doesn't combat it, I suppose. Also, one of the properties of the kidney is to stimulate vitamin D synthesis. So this is really interesting. We all know that the vitamin D is also known as the sun vitamin, right? But it's also interesting to note that the kidney participates in the vitamin D production as well. So even in the absence of sun, vitamin D is still produced in the body. It also produces the hormone erythropoietin, EPO. Okay, EPO produces red blood cells. Okay, which obviously you guys know the red blood cells, they deliver the oxygen from the lungs to the rest of the body. So I think that's pretty interesting. Now, in order to try to help your kidneys stay in the best possible shape, again, let's go back to the blood pressure. If the renin that produces the angiotensin is insufficient, or if there's insufficient action of the enzyme on the angiotensin proteins, then one very simple introductory approach to assisting with this is to introduce hydrochlorothiazide or some kind of diuretic. Diuretics, for instance, this hydrochlorothiazide, this HCTZ, which structure I'm showing here, is the 12th most prescribed prescription in the US, at least in 2016. So among all the medicines that are available in the United States, this is the 12th most prescribed. In fact, I'm even taking hydrochlorothiazide. to help regulate excess water that is produced by the kidney and that would be going throughout my body. So one of the ways that one of the primary ways that this does that it works, the mechanism of action here is that it reduces filtered blood volume by reducing sodium ion reabsorption. Okay, it competes with that with the chlorine receptor. Okay, so this is part of it. So if there's not as much sodium that can be reabsorbed by your body, then obviously you're not going to have as much swelling within the body. So that's one way that it helps to relieve excess water. So it competes with it with this chlorine receptor. You see it here in this molecule. You see you have, I don't know, you have some of these amine groups, right? You have 1, 2, 3 of them listed in this molecule. You have an overall non-polar character right in the middle with that aromatic ring, and then right off to the left of that aromatic ring is the chlorine. So that is actually one of the key ingredients there, the key substituents, if you will, in trying to combat this or kind of address this excess of blood volume by virtue of the water. So if it can inhibit sodium reabsorption, then it's going to be a better situation overall. But this is one of the reasons why, if anybody is taking a diuretic, well, guess what? It's going to stimulate you to relieve yourself. So it increases urine volume, also known as natriuresis. And the natria is coming from the sodium, right? Coming from the old term for sodium, which is natrium. That's why the chemical symbol in the periodic table is Na. So it derives from that. So it has some Latin roots there. Small molecules are filtered via membrane, usually urea, creatine, sodium, chlorine, and potassium. Okay, these are just all naturally filtered by the kidney. And from the blood to the urine, well, that's called dialysis. Okay, the small molecule, the solutes, in other words, from the blood to the urine, that's dialysis. Larger molecules are reabsorbed into the bloodstream and they can present problems. For instance, if you have a buildup of larger proteins or even cells. So dialysis is referring to small molecule solutes. For instance, the urea, sodium ions, chlorine ions, right, and even potassium. But the bigger stuff is, well, a bigger problem. If the kidney cannot dialyze, waste products, unfiltered content builds up in body, creating a toxic environment, and then artificial dialysis is needed. This is usually referred to as hemodialysis. Okay, and here is an image, this cartoon and this image are from your book. You have the dialyzed blood going into this this kind of artificial machine here, and then you have blood pumping out, right? All of this. You have, just what the cartoon says. You have the dialyzing solution. You have this dialyzing coil. What you want is to have that dialyzed blood going to the rest of the body. If your body cannot do that because your kidneys are not working, then you will be hooked up to a machine like this. Your blood will be introduced into this tubing, if you will, here. So the bottom, you see where it says dialyzed blood, and then you have blood where you have pump. Well, where it says blood, that's where your blood is going to be admitted. It's going to be pumped. Of course, there's going to be a dialyzing solution, which helps to extract some of the excess small molecules that are present within your blood. Your blood will continue to be circulated, and then it'll be reintroduced into your body so that you can have a normal, conditions, well, more normal physiological conditions, at least as they relate to the small molecules. This is a pretty serious thing, right? Because if you don't have a kidney donor, then you're going to have to be using dialysis as a permanent kind of thing. And this means that you're going to have to be regulating when you eat, and you're going to have to be making sure that you're always having your machine accompanying you, right, in order to be able to live, essentially. Without your kidneys properly filtering out these small molecules, problems obviously, arise. And So this is a very serious thing, and it takes about 20 minutes. So after you would have eaten something, you know, I mean, obviously it takes you some time anyway to digest the food or drink, you know, depending on the size of this. That can even take its in and of itself at least 20 minutes. That you can assume that anytime you eat, you're going to have to then, you know, if you have this kind of condition where you need artificial dialysis, that this is going to become a serious event, and you're going to have somebody to help you with this as well. So this is one of the ways where home nurses actually can help patients who are on dialysis, because this is not just a single person, one-man operation here. It's fairly involved, as you can see. So for those that are hooked up to a machine, usually in the meantime, they're trying to do whatever they can in order to try to find the replacement kidney. So here's an example. This was shown in more recently. I think it was about a year ago, maybe year and a half ago. There was an NFL player that was fine. He was doing fine. This is Armonte Bryant, and well, his kidneys started failing, and that completely changed his way of life. That's just one example. It can happen at any time in your life. You're not just necessarily born with this. You don't have to be old with this. You can be a perfectly healthy, strong person, and all of a sudden your kidneys fail. Even my hygienist actually has now donated her kidney to her brother, and this was something that the family knew about with the brother ever since a young age. His kidneys were always going to be needing to be replaced. But the thing about a replaced kidney is that it doesn't last forever. And you might be lucky to get 10 years out of it, maybe even a little bit longer, again, depending on what you're eating, depending on how well your body accepts that donor organ, the matching of it. I mean, just all these things, right? But replacement of a kidney is definitely going to be serious. So even if somebody in their 20s or 30s receives a kidney, you can expect to have that person can expect to have at least 2 or 3, maybe even 4 more replacements for the rest of their life. So very, very serious situation. So the kidney is not something to be messed with. I guess you know, this is where you know, they joke about it, I guess. Well, I don't know if they joke about it, but in boxing, you know, they talk about the kidney punches, right? You can't have a kidney punch because the kidneys are so serious that is an off-limit target area, you know, in that sport. You don't want to be doing too much damage to the kidneys for the obvious reasons that I'm going through. So another ailment that's related to poor kidney function is the production of uric acid, right? Uric acid, this is the small molecule that shows that a poorly functioning kidney will have kidney stones that can precipitate, or uric acid that actually precipitates. And so here's an X-ray image of kidney stone, right, that had formed, and that usually forms then along the ureter, right? You're trying to, where you're going to eliminate the tubing, your natural physiological tubing that connects your kidney to the bladder. So passing those kind of stones has always been regarded as very painful. Okay, here's an example of what those kidney stones might look like. And usually, this is going to be a mixture of different things like oxalates. Usually this is calcium oxalate, but they can be other things as well. They can be a mixture of, or hybrids, I guess, really, of some calcium phosphates, calcium carbonates, just things like this. So what is the risk factor that can lead to this gout or kidney stones? Whenever we say gout, that's also the swelling here. Whenever you see that on the foot with the uric acid in that topmost image, I know it's not attractive. That would be one example of what gout would look like. So what are the factors that can lead to this? Genetics are number one, okay? So if your bodies are already disposed to it, then that's something that you're just gonna have to combat with, or your patient, or whoever you know, right? Dehydration also. But remember, only increase water intake until urine turns clear. So some people who are overhydrating, especially if they're doing it with filtered water, run the risk of going back to that hypotonic state where there's just not enough of solutes like the sodium chloride, which sodium chloride is so necessary for our functioning that we need to have a bit of salt in our diet. So for those that are sweating too much because they're exercising too much and they're drinking too much filtered water, which may not have a lot of sodium chloride, and they're watching their diet, well, hypotonic situation can occur. So that's something to be very aware about. So you only want to, drink enough water so that your urine becomes clear, okay? You keep on doing that, then you run the potential risk of creating undue stress on your red blood cells and other physiological cells that you need for life, right? And also diets excessive in proteins, okay? Excessive in proteins, grapefruit juice, salt, dark leafy vegetables like spinach and such, because they're high in oxalate, as well as vitamin D. So just like with most things, moderation is going to be key. It has to be key. We can't say, well, if I just smoke one cigarette, that's going to be bad for you. No, it won't be, not long term. And actually, lungs can get healthy if you ever stop smoking. But the point is, it's the damage that is done over the course of time, whether that's drinking too much alcohol, even if it's low levels of alcohol, but if you continue to drink that every day for 20 years, your liver might have a problem with that. If you're, eating all these dark leafy vegetables like spinach, you're having that 3 times a day for breakfast, lunch, and dinner, right? Plus you're doing a lot of exercising, which you're dehydrating your body. You might be at risk for later on, eventually developing kidney stones. Grapefruit juice, obviously if you have too much salt and if you have too much protein. So again, moderation is the key for actually for most things. It's funny that it's, that saying kind of, appears here, but it's true. You can't have excessive stuff, entering your body, because other issues in your body can and will occur. All right, so this is where we're at. I think we're going to stop here, and what we'll do is we'll take up the next webinar series starting with solubility. All right, so thank you for your attention, and I hope this was interesting, and you can write to me or reach out to me if you have any other questions. Thank you.